So today, as we can see, we are going to look into the 8th part of selected classifier tour. So specifically, we started by using a naive-Bayes classifier last week. So where we went through some of the introductory aspects. So we look into what do we mean by naive Bayesian, how it works. Then we discuss example. So today we are going to continue from where we stopped. So last time we made us realize the simple Bayes theorem upon which the special one we are looking at is based, which is the simplified one. And the simplification is the assumption that the variables or attributes are independent of each other. Because if we have to make it to be dependent, which is the reality of life, it relates to what we call intractable problem in the theory of algorithm computational complexity of system. So we looked into it, and especially we discussed the 3 major steps that is often taken when you use a naive Bayesian classifier. The first step is to convert it to frequency table. The second one is to look at the likelihood table, create the likelihood table from the frequency table, and then you use the Bayesian equation to calculate the posterior probability. So, and then the decision is going to be taken by assigning the class of that particular sample will be the class with the highest posterior probability, which is going to be the outcome of the prediction. So it's as simple as that. So it's a probabilistic-based classifier. So we looked into this example last time. So we all see how we generated the frequency table, which is the way to start. You generate the frequency table, you look at outlook. This is the first attribute or first feature. We call it feature. So pay attention to that. We call it feature. We can also call it attribute. So we can call it also the independent variable. And also we can call it predictors. So several names for it. And then we look at it in reference to the target. So based on that, we are going to look at, okay, so there are 2 options. We have play golf, yes or no. So under the outlook, you look at sunny. What are the state of sunny? How many times do you have sunny as value for outlook and you play golf? You record it here, you record it here. So this is how we generated the frequency table. We also do it for temperature, humidity, windy, until you finish everything. So we had this, and we did also this simple example, how we can solve a very simple problem using this kind of naive Bayes. And then we move on. I remember also to calculate to create the likelihood table for each of the other attributes, temperature, and then we also solve. I remember we solved a problem regarding this. We solved this problem also using this particular example. So whereby these are the training sets. So this is assumed to be testing set. It comes later. You don't use it for training. This is testing set. It could be more. So you based on these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These 14 samples. So we create our model. So once we build the model, so create the frequency table, the likelihood table, and then we solve using the probability. So once the model is functioning, then we now use the model generated, the probability values we already have, we now use it to calculate what is going to be the posterior probability for this particular new sample. And then we did that also last time. We said we first of all look into the likelihood of yes, then we look into the likelihood of no. Likelihood of yes is very straightforward. So we have outlook, rainy, and it's yes. Temperature, mild, it's yes. And also humidity, it's normal, it's yes. And I mentioned that we only consider those values that are given to us. As you know that, you see, the air is given to us rainy. Rain is given to us. So we are going to ignore other values, overcast and the sunny, we ignore that for that outlook. So for temperature also, we only consider mild. For humidity, we only consider normal. For windy, we only consider true, because those are the things that are the value that are given for the new samples that we don't know the class it belongs to, which we call the training set or the validation set. So once we get that done, so we were able to calculate the probability for the likelihood of yes, probability likelihood of no. So, and finally, also we have the probability of the both put together. So once we have the two, then we normalize. We should do describe, because if you sum this probability, you can never get to one. So when you normalize the probability, you know the sum of probability must always be one. So you have here and here. So this one has the highest probability. So which means that the value we just classify is going to be categorized into yes, that is you go play golf. So we can practice and then change it and then make the value as the one we might need. So this is a very simple way. We actually discussed last week how we can solve problem. We can solve problem using naive Bayes. And we made it very clear that we just pass through this method so that we can see by our hand how we can do this thing. But in reality, like I said, machine learning is for all. This is my own belief about machine learning. It's for all. It's just like a tool. So you don't really need to go into this mathematical basis. You don't need to know how it works. So shortly after the end of this lecture today, we'll show us how you can use Weka, so which we are using for now, so to implement. So everything is there, it's already implemented. But we know some of us could be very inquisitive. We want to see, okay, how does it really take place? So, and for people also, especially who are mathematically oriented, they might want to think about, okay, can I also come up with an idea to improve the way these things are happening? See, there are a lot of open problem, unsolved problem, the issue of the independency and dependency that makes the classical naive Bayes theorem to be very intractable to solve. So a mathematician might want to come up and say, okay, can we do something to make it better? So this one is the sense of going into it in deep form. But in actual sense, when you want to solve your problem as a researcher, you don't really need to go into this depth. So the software is there for you to use to calculate all these things. But we're doing this so that we can have at least a little bit of background knowledge about what is really going on. So today we said we're going to start really from the zero frequency problem, because sometimes in when you prepare frequency table, see, it is possible that you have something that is zero. We added then, if you remember the frequency table we prepare for outlook, because it's zero here, it means whenever you have outlook and the weather is overcast, everybody there play golf. See, whenever you have outlook and the weather is overcast, if you look at it here, outlook, under the outlook, overcast, 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 overcast. So all yes. See, so in that case, no is going to be zero. So it means we have zero frequency. And when you compute based on zero frequency, then you know what happens if we have a case of, okay, you need to predict and then we need to check for the probability of that particular Z, with the one with zero frequency. So we need to avoid it because everything will be rendered zero. Everything will become zero. You know that. Zero multiplied by anything is going to be zero. So in essence, how do they solve this? So this is the concept referred to as the zero frequency problem. One of the unique ways to solve the problem is to add one to the count of every attribute value class combination. This is called Laplace Estimator. See, that's when an attribute value R2, for example, doesn't occur with every class value, that is, play golf is equal to no. So in this case, we need to add 1, 1, 1 to everybody. We can't add 1 to this zero value alone as mathematicians. As in mathematics, we were taught this. So they say we didn't do anything. So when you want to solve your problem, you say x is equal to, let's say x minus 2 is equal to y. So you want to find the value of y. So you say you should add 2 to both sides. It will be x minus 2. Excuse me. Yeah, just trying to remind us of our simple either arithmetic or mathematics. So when you say x minus 2 is equal to y, so plus 3. So, and we want to solve for x, they say, okay, x minus 2 plus 2, y plus 3 plus 2. We add 2 to both sides. So mathematicians says we didn't do anything. We're just adding the same thing to both sides, which means this is going to go, we're going to have x is equal to y plus 3. So y plus 5. So in similar vein, we cannot just add 1 to this 0 frequency. So we have to add 1 to everybody. See, you have to add 1 to all other frequency values. So otherwise, it will not be okay. So we add 1 to everybody. So by so doing, we are going to avoid the frequency, 0 frequency value, which is actually a big problem whenever we use naive Bayes. So in that case, this is a 0 frequency problem example. So let's say you have, this is simple problem again. You want to see is the time zone and the EU zone. You have spam. The spam, is it yes? Is it a spam email? This is a simple classifier to predict if an email coming in is a spam or not a spam. So, which is one of the very interesting cybersecurity problem these days. So as a lot of spammers send different messages, you click it, your own company can be down. The whole company could be down. So can we actually identify this email is a spam before it enters your inbox? Because there are some people that anything that enters their inbox, they click it before they even read the content. So it's not everybody that is alert to what is he or she is reading. So spam filtering will be able to assist us to prevent such people from even seeing the spam in the first instance. So that they don't run into trouble, and not just run into trouble, they can put the entire company into trouble. We've heard of a simple click of an email that led to the down of all the system in the whole company, and took them weeks before they could actually come back online. And that means a lot of billions of losses on a daily basis. So to prevent this kind of thing, email spam filtering is a very, very popular and most sought after model-based system development these days. So for this example, you can see here, so when you have 0 frequency, so what you have to do, because this one is going to have 10 out of 10, it's going to have 1, while this one is going to have 0 probability. So probability that the time zone is EU, given that the spam is yes. For US, given that the spam is yes, we're going to run into trouble in this case. So what should we do is we add 1 to every value in this table when you are using it to calculate probabilities. So then it becomes 11, 1, 1, 6. Pay attention to that. So we increase the entire number, not just only 1. So otherwise, because like I said, mathematically, it doesn't make any sense to just increase 1. Where are we bringing that 1 for? But very mathematically, we added 1 to everybody. So we are not cheating anybody. We are not doing anything. It's just okay. So therefore, we have 11 here, 6 here, 1 here, 1 here. Then we can calculate the probability without actually getting 0. So this is one of the way that the 0 frequency problem in naive Bayes classifier is often resolved. Now, so another simple fact about naive. So for that thing we're going to look at, then before we look at the practical example of how to use it, sometimes we might have numerical predictors. See, numerical predictors. So what do we mean by numerical predictors? When we say predictors, remember I said attributes. I said attributes, another name for attributes, feature, independent variable is also predictor. And I think I clarify it in one of my, because I've seen people used to make mistake. They said, I develop a predictor. The model you build is not a predictor. It's a prediction model. It's a prediction model. Predictors actually are the variables that are used as a means to be able to build the model. So our attribute like the outlook, like the temperature, these are the predictors. So when we have numerical predictors, if you look at the predictors we use here, you see that the values are not numerical. These are categorical. You can see this is the predictor number 1. rainy, there's no number there. So this is what we mean by when we say that numerical predictor, it means the value inside these ones, they are like maybe 20, 40, 50 or 50 point something. So when they have numbers, this is what we call numerical predictors. So the numerical variables need to be transformed to their categorical counterpart through what we call the Baining process before constructing their frequency tables. So unfortunately, when you work with naive Bayes, this is probability. So you can't work with the number directly. You have to convert them, the numerical variables, to their categorical counterparts. That is, convert it to form. Just like what we used to have when we have group data in statistic. You know, when you have group data, we have several value of student test result. 2, 3, 4, 10, 15, 17, 25, 28, 32. So we have to convert them into from 0 to 10, you see, from 11 to 20, from 21 to 30. This is what we call binary. See? So you have to convert it. So that this is going to be like more of, we are converting to like category now. We have category from 21 value to 30. We count there. How many of them are in that place? So we have to have frequency value for that. How many between 0 and 10? We have the frequency value. How many between 11 and 20? We have the frequency value. So this is how you deal with numerical predictors. So in which case, if you have, of course, the software will do it for you automatically. Yeah, it's going to do it for you. It's going to create from the values and generate this particular target. But then a rule of thumb says that if your data is really numerical based, perhaps you might need to start thinking of other classifiers to try out. And that is why one of the strong points of naive Bayes is that because it's more straightforward when it comes to categorical, it's very powerful when we are doing text classification. When you do text classification, we're going to see it, but then it has the capability to do. Now, so this one option, the other option we have is using the distribution of the numerical variable to have a good guess of the frequency. So if you don't want to do this kind of binding, where we have to partition the data into different groups to make it look like categorical, then we can also try to see, okay, can we use the distribution of the numerical variable so to now make a guess of the frequency? For example, one common practice is to assume normal distribution for numerical variables. We can assume normal distribution, but sometimes it doesn't work. So not every data will follow normal distribution. Just like in some grading, after grading, they said the grade of the student should be normal. So the grade can be normal if we are not using a fixed grading system. If you are using fixed grading system, it's very difficult to have normal distribution. So, but when you are using relative grading, so whereby after grading the student, you have to make a curve to assign them grade. Sometimes in a course, the A+ might be very low because no one actually got high mark. In another course, we can have a situation whereby to get an A, 95 might not even get an A+. Maybe 97 will be A+, because there are so many people who are on the other side. So we use this kind of curve to normalize the data. However, if your grading system is fixed, if you get 95%, you get A+. If you get 90 and above, you get A. Then you cannot guarantee that you're going to have a normal distribution, because in such data set, what if half of the class decide to get 95? So, and less than half of them again got less than 60, meaning F. In between, so you're going to have a totally different distribution of the value. So this is why sometimes relying on this idea of using the distribution, using normal distribution might not really hold, depending on the problem we are solving. Now, so we said the probability density function for the normal distribution is then defined by two parameters, which is mean and standard deviation. If you go for this option, then a little bit of difference is, then we calculate the mean, the standard deviation for this particular normal distribution you have selected, and then you can then apply it to calculate the probability, because what we just need to get is the probability. So since you don't want to convert your data into groups, for example, binding process will have said, okay, between 86 and 70, between 70 and 90, but we don't want to do that. We want to just assume that it's normal distribution. Okay, follow it, calculate the standard deviation, calculate the mean, and then use the formula to calculate the probability of humidity, given that this is 17 and years. So we are going to do it for whatever samples you are given to calculate. So calculate the probability of playing a golf if the humidity is 70, or if the humidity is 70, or sorry, 74. So in that case, we have to deal with humidity that is 74, given that it is yes, using this particular formula based on what you've calculated, the distribution you assume, and then we can get the probability. Then through normalization of the probability, you'll be able to know which of the category got the highest probability. Is it yes or no? So this is how we work with numerical predictors when you use naive Bayes classifier. So that is another special case. But then the categorization is a little bit more reliable. Of course, it depends on the data set you have, actually. If you can guarantee that your data set is normal distribution, or you know the distribution of your data, then you can go for the second one. In which case, you don't need to do any categorization of your data. You just deal with it directly as we had. Now, so we said the naive Bayes uses similar method to predict the probability of different class based on various attributes. And it's mostly used for text classification. Like I said, naive Bayes is very, very popular with text classification. So, and also with problem with multiple classes. So when you have multiple classes, like you have, we've been dealing with example like yes or no. Sometimes we have several number of classes like class 1, class 2, class 3, class 4, as many as possible. Like if I want to predict what is the grade my student will take in my course, so I have from A plus A, B plus B, up to like maybe F. I'm talking of like 9 categories. So in this case, this is multiple. And from my experience, the more the number of classes, the more challenging the modeling becomes actually. So if you can have 2 classes, you get very good accuracy, 99, 98. The moment you increase the number of classes, it goes down. So that is why sometimes you might need to use divide and conquer. You see, divide the problem into two classes, solve it, and then combine them gradually. There is a principle like that. You divide into two classes and then solve it, 2, and then come back later and combine it. And this is one of the methods that support vector machine used to make it also get better result. We'll discuss about that one later, inshallah. However, when you have multiple classes and you don't want to do all this divide and conquer, then text naive Bayes classifier might be an option for you to quickly look at. Of course, we are not saying it's the best for text classification, but it's often used for it and often get very better result if you look at literature. But however, the principle, I always tell us, let the data speak. It's very important. So that's why if anybody tells you the best method to be used for a particular problem is this, it's against the principle of machine learning. Yeah, if all things being equal, yeah, let us say all things being equal, like the economy will say. So the rule of demand and supply, all things being equal. Sometimes it doesn't really work. So because the data set could be different from what we are used to. So we have so many data now on social media following different patterns. So nobody can really guarantee if this is going to work. For example, like a student few days ago, they were solving a problem and then they decided to search for hyperparameter in a range between maybe 20 and then 70. And then they search for it and said, why did you limit yourself to 20 to 75 range? He said, because we read it in a particular paper that they recommended that it's one of the best range. I said, well, that's a recommendation. I said, from your result now, I can see that you are choosing local minimum. You see, sorry, local maximum. We want global maximum. You see, when you are searching for the best, see, sometimes it goes, this seems to be the best. Meanwhile, there could be another best here. You see, if you stop at this point because this one is up and coming down, then you are stopping at what we call local maximum. Meanwhile, there's a global maximum, you can still get better result. So this is why when you're searching for parameter, keep it open. Irrespective of the advices people get, they give this advice based on their own experiences. But sometimes, like I said, let your data speak to you. The data should tell the system what is going to be good for the data. And that is the essence of data mining, machine learning, data science we're talking about. So we want the data to really look into the data, to really get feedback from the data. The data do speak. So the system now, the data do speak, but as human beings, we don't understand the language of the data. This is why machine learning will look at the data, then the data can say, okay, this is how I am. These are some of the information you can get from me. And if you are not able to understand the language of the data, you might need to start adding together multiple classifiers. See, maybe one classifier is not enough to understand the data. Okay, good. Then add more in what we call ensemble. You remember we already discussed ensemble extensively in some of our previous videos. We can check it out. Sometimes you might need to combine different models to be able to get what the data is really saying more clearly. Now, so these are some of the special cases we have to take note that, okay, although naive Bayes is very, very highly reputed for text classification, and when you have multiple classes to predict, you go for it, at least as a starting point, because one of the very simple algorithms that I do recommend for people, k-nearest neighbor, naive Bayes, decision tree, whenever you are starting a application, quickly use them because they're very straightforward and you don't really need much parameter optimization, especially for naive Bayes. There's no parameter optimization for it. See, you just click it and then you start modeling. However, we have towards the end, we say we have types of naive Bayes. There are a couple of types of them. We have the multinomial naive Bayes, which is mostly used for document classification problems. So whether a document belongs to a category of sport, politics, technology. So these days now, you just go online, when you search, you try to say category. There are lots of application of text categorization. So the features or prediction used by the classifier are frequency of the words present in the document. So sometimes when you search, you want to see, okay, is this document sport? Is this one about technology? They group it together. You can go to Google search now and type, I want document related to sport. How do they know this document that are related to sport? There are so many documents online. So they use some of these multinomial naive Bayes to do the classification, to predict, okay, this one, because there are so many words that are related to sports in this document, I think this document should belong to sport. Sometimes I think there are so many words related to politics, this one should belong to politics. So they already train a machine learning algorithm with huge data that some of these search engines now, they are using. So whenever you type something, they quickly, in the back end, they quickly launch the machine learning algorithm to quickly search, okay, where is this particular one going to belong to? And they can give you the appropriate one that is correct. This is one area where we use the multinomial naive Bayes. It's used for document classification. We have the Bernoulli naive Bayes, which is similar to the first one, but the predictors are Boolean variables. The difference between this one and that is that this one uses Boolean variables, that is, variable that has yes or no as answer. You know that? So it's either true or false. See, the variables are having true or false. It works just like this, but the only special case is the predictors are not like the previous one. They only use true or false as the value of the predictor or attributes or what we call the features. And the parameter that are used to predict the class variable take up only values yes or no. For example, if a word count is in the text or not, you can see. If a particular word occurs in the text or not, you know, it's different from this one that we count. How many number of words that are in this particular document, the frequency of the words, which one appear more? But here it's going to ask, is so word, is it there or not? Is yes or no? This is what we mean by Boolean variable. So they're going to have something like yes or no, this word is there, yes or no. This is how Bernoulli naive Bayes works. And the last one is the Gaussian naive Bayes. Here it is used when the predictors take up a continuous value. The example I gave earlier. So when the predictors are numerical and they are not discrete, so it's good for making prediction from normal distributed features. If your features are normally distributed, you are sure, then it's good to go for that. So the naive Bayes to be used there is known as Gaussian naive Bayes. So in that case, it's not text, it's not categorical, but it's number. And you don't want to, you still have the option of converting your number back to text. I mean, back to categories. Yes, yes or no, or back to even text. What is the category? Like the samples we gave to us before. You can always convert your data to be hot, mild, cool, because you just need to say that, okay, hot is temperature between 40 and 50. It's very hot. Between 30 and this is going to be hot. So you can always convert your numbers. But if you don't want to convert them, then you go for the Gaussian naive Bayes to solve your problem. So these are some of the options that are available under the types of naive Bayes you can use. As for the pros, some of the advantages of using naive Bayes is very, very simple from my own experience, very simple and easy to implement. By the way, it has zero parameter. One of the challenges of machine learning is parameter optimization. See, in the parameter optimization, you might end up using wrong parameter. If you use a wrong parameter, for example, in SVM, we have the polynomial, we have the Gaussian, and so many other, the RBF. You might use polynomial for a problem. You got like 99% accuracy. Mashallah, very great. So Gaussian, for that same problem, is getting like 40. But next problem you got, you use polynomial, it got 50. But you use polynomial for this Gaussian is used for this new problem, you got 98. So it means if you wrongly settle for a very wrong choice of parameters in machine learning, you'll be missing a lot of important facts. And that's why I used to tell people, tell my students, that you need to be fair. You need to be fair to the algorithm. Being fair to the algorithm means you need to exhaust all the possible parameters that you can search. Because if you just conclude that SVM is better than neural network, ANN. You search for the parameter of SVM, but for ANN, you didn't search for the parameter very well. You just use the default parameter. I said, this is not fair. And that is like lying. You are claiming that SVM is better on this particular problem. Meanwhile, you did not treat them fairly. However, for naive Bayes, it's an advantage in that there is no parameter search for naive Bayes. It's so simple. So you don't need to do any waste of your time on parameter search. Just put in your data and then let it go. So it needs less training data. That's another advantage of naive Bayes. When your data set is not much, why not give it a try, actually? It needs less training data because it's based on probability. It handles both continuous and discrete data. Another advantage, there are a few that only work on categorical, but this one can work on categorical and also on continuous. Continuous being numbers, real numbers, why this one is categorical, like male, female, sunny, like the sample we gave. It's not sensitive to irrelevant features. Another advantage of it, not very sensitive to irrelevant features. Even when you use features that are not that very sensitive, it still go with it. Like the example of temperature, one of our participants, Dr. Said, mentioned this last week. We knew under decision tree that temperature is not really important, but naive Bayes use it without even any issue, where you see achieve your intended result. Since it is fast, it can be used in real-time prediction. This is another advantage of naive Bayes because it's faster, so you can actually use it in real-time prediction. Because once you build the model, so the next thing is just to quickly calculate the probability, multiply them, and then you get your result out. So because real-time prediction is very important. Sometimes we solve a problem. I remember one of the problems I solved a long time ago, we call something extreme learning machine, ELM. It's one of the type of neural network. It's extremely fast, by the way. They call it extreme learning machine. It's a special type of artificial neural network. I also had SVM for the same problem. But SVM was getting like 98%, while this guy was stuck in 96. See? Based on, I said, okay, SVM can go for the best. However, I recommended this one for online. If you want to solve this problem in real time, SVM takes a lot of time, but ELM is very fast. So I recommend it, even though there is 2% difference, if you want to go to real time, because real time means as event is happening, you need to predict. So there's no time for time wasting. So that's why sometimes you might need to, it depends on what's the goal of the client that requested you to solve this problem. If they're really interested in time, time is very important for them, then you might need to go for something that's going to take lesser time, even though you might need to compromise the accuracy. So that's called the real cost of what is more important as the goal of the project. Now, sometimes we solve problem, we recommend this one. If you're using it offline, use this one. But if you're using it real time, then go for this one. 96, 98, it's a little bit close by. But with latest technology in hardware now, with parallel processing now, we can actually have our machine learning algorithm to run in parallel to increase the speed. So in that case, we might still be able, if the client is ready to purchase like GPU, very powerful machines, then they might be able to go for better one because they're going to have a very strong, faster processor to deal with the algorithm. Otherwise, if they want to use the standard system they're using, then they have to compromise the accuracy. So when you are faced with real-time product prediction, then naive Bayes might be an option for you to quickly check because it is reportedly very fast. It is highly scalable with number of prediction and data points. So you can easily add data points to it. It's just a matter of recalculating the probability and then it goes on. It also performs well in multi-class prediction. Yeah, it's an established fact with that. It's just a matter of calculating probability for each of the classes and then the rest is history. As good as it looks, very simple. So the challenges involve the categorical variables, you see. The issue is that if categorical variables has a category in test data which was not observed, we call this zero probability problem. We already explain it, zero frequency problem. To solve this also, we mentioned the technique that used to be used, which is called smoothing techniques. And under these smoothing techniques, the simplest one is known as the Laplace estimation, which we also described earlier. So this is one of the challenges with it because you have to look out that, oh, is my data having zero frequency, which is very easy to get actually. So which means it could be a problem if you don't know it, because you end up having zero probability always, which is going to render everything to zero. Another limitation of naive Bayes is the assumption of independent predictors, which is a very big issue here. It is presently assuming that the predictors are independent, but in real life, it is almost impossible that we get a set of predictors which are completely independent. That is, I want to predict my student performance. I'm looking at the attendance. I'm looking at the grade in the previous prerequisite course. I'm looking at the student history of any ailment. I mean, some of these attributes, they are connected to one another. If a student is sick, maybe the student was sick before. He said, yes, he was sick before. He has some ailment. So his ailment might be affecting or making him to be having attendance issue in class. So in reality, you see that predictors or features, they are connected to one another. So, but now for naive Bayes, we cannot solve it. We cannot solve the full Bayes one for now, because it is intractable. So we go for the assumption that we close our eyes that the variables are not connected together. They are not dependent. This is a very big weakness of naive Bayes, but at least that is what we have for now. And even still with that particular weakness, it's still getting very excellent results, especially when it comes to test categorization, multiple classes, and so many other applications that they have used it for. But for sure, this is an open problem. A mathematician might want to look in that direction to see what can we do to really use the actual Bayes theorem to solve our problem. That would be really fantastic if it could be solved. But because of the computational complexity, people settle for naive, that just assume that there's no connection between this and this. Treat them as independent. But in reality, they are not dependent. But we have to close our eyes for now. This is the best we can have as far as naive Bayes is concerned. So now, it's almost, yeah, we have a few minutes more. So before we go to question and answer time, so I think we are going to look at it. We open the Weka and see where do we find it in our Weka application, so in case we want to use it. So at the end, we say some of the applications, like I said, real-time prediction, some of the area that are popularly, that we have naive Bayes is popular with, real-time application. Because I've explained this one. Naive Bayes is an eager learner, it's an eager learner. So at the beginning, we classify learners into eager learners, okay? So, and those ones that are not. So they learn quickly and it is very fast. So when you are talking of real-time prediction, it's an option. Multi-class prediction also, you go for it. Test classification, spam filtering, sentiment analysis. Like sentiment analysis these days is getting really popular. When the government or anybody want to get your opinion, usually when people give you, if they give you a kind of what do you call it? we used to fill it questionnaire. You see, when you want to get questionnaire from people, when you give them, they are very busy. So they don't want to say no to you. They end up saying yes, yes, yes. They just fill it at random because they don't want to say no to you and they are busy. So sentiment analysis is saying we don't need to do this anymore. Just go to their social media. You can get better and more reliable opinion of people when they're chatting with their friends. Most likely they're not going to lie, especially if you're asking your staff to tell you something about your company and you are giving him the document. If you say no to your whatever, he will be afraid that if this guy knows I'm the one doing this, maybe they will not like me. But with sentiment analysis now, they go online to your social media to see what you want. In fact, recently now they are using it to diagnose mental illness. See, because some of these are some of the challenges to tell somebody you are mentally ill or asking him. The moment you ask few questions, he will be angry with you. They go to sentiment, they use sentiment analysis now to try to see the way people chat. From the chatting you see from people, we can predict who is likely going to have mental illness or not. And so many application areas. So Navy has actually proven itself to be very strong when it comes to text classification, spam filtering, sentiment analysis, and a host of others. So it means whenever we have anything that has to do with this, Navy could be a point of call for us. However, I'm not saying it's the best because I always mention this. Anybody that say one method is the best, he doesn't understand how machine learning really works. But I'm saying it's one of the areas to beam your light if they are related in that area. And also it is very simple. So you have nothing to gain, you have nothing to lose by trying it first. And also in machine learning, one of the principles in machine learning we alluded to earlier was that we should always start from the smallest. Start from simple algorithm. You see, like KNN, naive Bayes, decision tree. Start from simple algorithm before you start going to ANN, support vector machine, and host of other complicated or senior or more superior algorithms. Because sometimes the simple one will solve it, even the bigger one might not be able to solve it. See, as we say in my local dialect, I don't know how I'm going to translate this. So that is sometimes we want to put the hands of a young boy cannot take something from the tall place because the hand is not going to get there. But at the same time, when you want to take something from the jar, you have a small jar, very small mouth. You see, the grown-up people cannot take something from the small jar, but the baby can help you put their small hand inside it and then bring it out. Which means that both the small one and the bigger one, we can all collaborate to solve problems together. I think this is the meaning of this aphorism. So, because I've always seen people, when they have a small problem to solve, they go for deep learning. No, it doesn't work like that in machine learning. Go from the simple to the complicated. It is when the simple one fails, then you go for complicated method. Otherwise, it's sheer waste of time and energy, because you find out, you can find out later that even though you spend a lot of time using the more sophisticated algorithm, you couldn't get better result. You finally come back to simple one, and you find out that the simple one are giving you better result. It happens, it has happened, and it will continue to happen. So that is why we advocate, start from simple method, then gradually go to more sophisticated method. And also recommendation system also is another very big application areas that now base is being put to or has been put to and will continue to be put to. So where you have kind of, you can use it for several things. When you buy something online, they try to recommend people bought this, also bought this. People bought this, also bought this. This is called recommendation system. They use for medical and so many other things. You want to look for the appropriate hospital to visit. You see a lot of recommendation based on what to search, based on your history, based on the country you are staying presently. So these are some of the applications, and there are so many other application areas they are put to, but at least considering the special cases of navies, then I think these are some of the areas. And because of our time, I think this is a good place to call it a day. We're going to take a couple of questions. So thank you very much for the time. And we continue from a nice time. Thank you very much.